Hi everyone. So welcome to lecture 12, which is going to be about linear algebra. And what we're going to do in this lecture is significantly expand on the content of the book, which you can find in the notebook that accompanies this. And we're also going to trivialize a lot of the heavy computational algorithms that you learned in your early linear algebra classes. So the theory of linear algebra is extremely important, and the ability to do those computations is extremely important. What turns out not to be so important is the ability to do those computations by hand. This is perhaps the area where computers have made the greatest contribution to modern mathematics, is in making the overwhelmingly tedious and error-prone computations of matrix analysis into consistent and fast executions. So we're going to start by talking about matrix operations, and in particular, how you put a matrix into Mathematica. We've already seen some of this. So the place that we start with matrices in linear algebra is to realize that there's no difference between a matrix and a list. The way that Mathematica stores the base information is the same. So we could look at something like A is equal to 1, 0, 0, 1, 0, 1, 1, 1, 1. And that's a matrix. Each sublist we think of as a row of the matrix, and there's 3 of them, and they all have the same length, so that's important for a matrix, is that you have the same number of elements in each row. And we can actually visualize that as a matrix by using the command matrix form, which we've already seen. And from this standpoint, Mathematica just treats A like a matrix. Now, I want to point out here that we have to be careful about using matrix form. All of the operations that Mathematica does with matrices exist on the lists that are defined this way. We don't want to define something in terms of a matrix form because that's a visual representation of a table. Okay? So if you define a matrix and you use matrix form, what's going to happen is Mathematica won't do any of the algebra that it's supposed to do because it doesn't know how to manipulate the graphical representation matrix form, but it does know how to manipulate the underlying table. So one of the most irritating things to do by hand is to multiply matrices. So let's just suppose we cook up another matrix here, 2, 1. In fact, let's do something like random integer, and let's suppose that I pick numbers between 0 and 3, and let's make it a 3 by 3 matrix. This is a thing we can do. So if I want, I can put this into matrix form. Now, A and B are matrices that I can multiply. If you just wrote down A times B, you're not going to get the answer that you want, because remember that what Mathematica does when it sees something like A times B is it thinks, oh, you would like me to act entry by entry. So if you do that, you're going to get a lot of zeros because what you're doing here is you're multiplying a 1 times a 0 and a 0 times a 1 and a 0 times a 3 and so on. Okay, so that's entry-wise multiplication. It's not matrix multiplication. If I want to use matrix multiplication instead, what I have to do is use something called the dot product. This is how Mathematica encodes matrix multiplication, is with the command dot. So if instead we dot A and B, we'll get precisely what corresponds to the matrix multiplication that we learn in linear algebra. There's a shorthand notion for this, which is if I can write down A dot B with a period here. Oops, where'd my B go? So A dot B performs the same operation. The next question you might have is, how do we deal with vectors? So the book actually starts with vectors, but how do we start with vectors? How do I think of vectors when I'm working with Mathematica? Well, I think of vectors as a matrix with either one row or one column. Now, it's sort of irritating to work with column vectors. Column vectors are the standard tool in mathematics. We think of vectors as being columns. In other fields, vectors are usually thought of as rows instead. But for us, for the purposes of this class, we're going to use the typical mathematical convention of thinking of vectors as columns. And if I want to encode a column, I have to make a list that has rows of length 1, and that means a lot of braces. So if I wanted to code a vector x, I might have to write down, well, first there's a 1, and then there's a 2, and then there's a 3. That's a column vector. So we can put x in matrix form, and we can see that it's a column vector. So let's look at what a row vector would look like. So y is a vector consisting of a single row, 1, 2, 3, And that's what a row vector looks like. Very easy to input a row vector. You can check to see that it actually represents as a row vector by feeding it into matrix form. And there you got the row 1, 2, 3. Now, there's a trick that you can use for defining column vectors, which is to use row vectors but then transpose them into columns. So I don't like entering vectors like this. It's a lot of braces. It's irritating to stretch my fingers to get there. So what you could do instead is you could use the command transpose. And if you transpose y, then you're going to get a column vector. So it's a very typical trick when you're working with these matrix quantities to define, anytime you want to work with columns, you start with rows and then you transpose them. All the rest of the algebraic operations work exactly the way we'd expect. We can take a plus b, we can take a minus b. You have to be careful here because Mathematica will actually let you do a divided by b. It's going to be angry here because the matrix has zeros all over it, but this is not a well-defined thing. So in general, don't do this. 1, it's entry-wise. And 2, division of matrices doesn't make sense. So what other typical operations do we have when working with vectors and matrices? Well, you might want to know how long a vector is. So in that case, remember our vector x here is 1, 2, 3, we can actually take the norm of x. So norm of x just computes the typical Pythagorean theorem. To get a better grasp on how these operations are working, we can use a symbolic expression instead. So vectors are easy to build out of tables. This is not quite what we're after because it looks like just a row. So if I surrounded this with more braces, then I'm going to get a row vector. And I could go one step further and I could transpose this into a column vector. Pretty typical thing to do. Now if you compute the norm of z, you're going to get the expression. Now what are the conjugates doing in here? The conjugates are in there because norm thinks that it's possible that a1, a2, and a3 are complex numbers. And this is what the norm looks like when you're doing complex numbers. If you impose the further restriction that all the ai's here are elements of the real numbers, this would look like the typical a1 squared plus a2 squared plus a3 squared inside of the square root. One of the core applications of matrices is in giving a very efficient way of solving linear systems of equations. And this is another area where Mathematica is very powerful. And there are some tools that we develop by hand when we're learning to solve linear systems that are much easier to do in a computer system. For example, row reduction. So some things that come up when we're doing linear systems are things like, we really like to be able to know how to row reduce a matrix. That's the first method that we learn when we learn how to solve a linear system. We also learn a method of working with inverses. So if A is an invertible matrix, then we learn that we can cancel the A off one side of the equation by multiplying by the inverse. So those are both things that are very easy to do in Mathematica. So let's actually look at what some of those are. Here was our matrix A from before, and here's our matrix B. So some things that came up when you learned how to solve linear systems were being able to row reduce a matrix. Well, it's pretty obvious that Mathematica is going to have a row reduction command if you put your brackets in correctly. Okay, so A row reduces to the identity. If A has an inverse, and we know that it does because it row reduced to the identity, then we can just compute the inverse directly very quickly, which is a nice thing to be able to do. Another tool that we learned for working with matrices was the determinant. So determinant is easy to compute, again, if you use your braces correctly. So the fact that this statement is -1 and the matrix row reduces to the identity matrix are both operations that tell you that the matrix is invertible. So you do remember the invertible matrix theorem, I hope. So once you have that, it's very easy to work with a linear system. So suppose that you're dealing with something that looks like AX is equal to B. Okay, so let's look at solving a problem of the form AX is equal to B. So one way to do that is with the inverse method that we talked about. We already know that A is an invertible matrix, right? Because the determinant of A was equal to -1. So let's suppose that X is unknown. So X is unknown. And let's just define some quantity B. Here's our matrix A. Let's define B to be equal to 1, 1, 1. And I want to solve AX is equal to B for the unknowns X. Well, that's the same thing as writing down X is equal to A inverse B. And I know A inverse exists because its determinant was not 0. So I could perform that by writing down X is equal to the inverse of A times B. Dead easy. In fact, ridiculously easy in this case. And I can check to make sure that my answer is correct by just computing A times X. So A times X is 1, 1, 1, which was B. So I've solved the problem with this inverse method. Another way that we learned is with row reduction. So row reduction actually is going to allow me to show you a trick that you can use for manipulating matrices. What I'd like to do is make an augmented matrix. If I want to work by row reduction, I have to make an augmented matrix. Okay. So to make an augmented matrix, I really like to stick an extra column on the end of it, but that's hard to do because of all the extra braces and things that are running around. So a typical trick in Mathematica is not to work on the original matrix to make the augmented matrix, it's to work on the transpose because rows are easier to manipulate than columns are. So we could do this. What is A3? What is the third entry of A? Well, it's 1, 1, 1, which should be obvious because it's the third row of A. Well, that's very easy to call, and it's very easy to add to. So what I'm going to do is I'm going to work on AT, and AT is going to be equal to the transpose of A. Okay, so there's A. Here is A transpose. To remind you, the transpose of a matrix takes the columns of a matrix and turns them into the rows. Then what I'm going to do with the transpose is I'm going to glue the information from B, this information, I'm going to glue that onto the matrix as the last row. If I have B as a row vector, I can glue it onto the transpose of A as the last row. That's very easy to do. So let's write down B transpose. So B transpose is going to be equal to the transpose of B. So now I have A, and so now I have the transpose of A, and I've got the transpose of B, and I want to glue the transpose of B onto the transpose of A as an extra row, and then I'll just turn the whole system back into what I want, the augmented matrix, by taking another transpose. So it's easy to do that because you could just write append to A transpose B transpose. Let's make sure that it did what we want. Oh, I suppose I should call this something. I could call it aug transpose. So let's look at A transpose in matrix form. And let's look at aug transpose in matrix form. So you should notice here, okay, you gotta be careful. So I have the information in B transpose stored as a row inside of a matrix, but it's just the row that I want stuck in, so I should have used join. There we go. Okay, so now we look right. So this is correct because I've taken my A transpose matrix and I've glued my augmented matrix on as the last row. If I take that and I transpose it back, and I look at what that looks like, then you can see that that is precisely what we wanted. We've taken A, and we stuck this column onto it, B, as an augmented column. So this trick where you transform the system by transposition and then work with the rows and then transpose back is a very typical computational trick when you're trying to add columns to a matrix or select out a column, for example, in Cramer's rule, which would be an exercise in the notebook, that it's much easier to work with rows than it is to work with columns. Okay, so don't be afraid of transposing the system in and out of the shape that you want so you can work with rows instead. You can always come back. So now that we have our augmented matrix, and I want to solve the system, and I just row reduce it. And to make it easier to read, we can put it in matrix form, and that tells us the answer. That x1 is 1, x2 is 0, and x3 is 0, right? So this kind of approach to solving linear systems is dead typical. Okay. All right. Now there's other methods that will be covered in the notebook as well. So typically in linear algebra courses, after we've learned something about the invertible matrix theorem and all of the different ways that we can look at inverses in solving linear systems, we move on to more geometric descriptions of matrices. And that includes things like which spaces do they hold invariant under multiplication. So that is where we're thinking about matrices as representing linear transforms. So I want to show you in this section a little bit about how to generate matrices that satisfy some certain formula in their generation, and then how we can start thinking about eigenvalues and eigenvectors and how that could be used to form diagonalizations of matrices. Okay, so some of the big ideas from the second half of linear algebra. So the first thing I want to talk about is the function array, which is a way of generating a matrix from a function where each entry is given by some function in I and j. So remember that we think of a matrix as being something like the matrix A could be thought of as A ij where I and j run over some, so I runs from, I and j run from 1 2 3. Okay, so what I mean by that is this would be a 3 by 3 matrix that looked like, well, it would look like this. So I can have a table, and let's suppose that I make my table to be ij, and I run I from 1 to 3, and I run j from 1 to 3. That's a pretty typical way of thinking about what the structure of a matrix is. Put this in matrix form so you can see. So these are the elements that correspond to positions inside of a matrix. So the 1 1 element is in the upper left hand corner, the 3 3 element is in the lower right. The first index tells you what row you're in, the second index tells you what column that you're in. So if I have a formula that generates a matrix, I can do that using a function called array, and that is where the aij's are dictated by their positions. So for example, I could set up a function that does the following. It takes a variable in and it adds it to a second variable. And let's suppose that we run this on a 3 by 2 matrix. Then what we're going to get here is a 3 by 2 matrix where each entry is the sum of its indices. Okay, so this is the 1 1 entry, which adds to 2. This is the 1 2 entry, which adds to 3, and so on. So if you have a formula for defining a matrix, and that happens frequently, it's very easy to generate that matrix using the array function. That's the natural function to use in that context. The last thing I'd like to talk about in this brief introduction to linear algebra, and there will be a second video on more sophisticated concepts that follows this one, is to remind you guys about the diagonalization of matrices. And in particular, there's something called the spectral theorem, or the theorem of diagonalization, which tells you when a matrix can be diagonalized. The big thing that I want you to remember is sometimes a matrix can be diagonalized and sometimes it can't, depending on the relationship between the eigenvalues and eigenvectors of that matrix. Now, eigenvalues and eigenvectors are concepts that I'm going to assume that you remember. The basic idea there is that you are looking at a setup where you have A times V is equal to lambda times V. For some lambda, which is the eigenvalue, so lambda is the eigenvalue, and V is the eigenvector. And you do a lot of study. I should be careful here with this dash. It's not subtraction. Lambda is called the eigenvalue, V is the eigenvector. Okay, and that a big part of the study of the structure of matrices is has to do with finding the eigenvalues and eigenvectors and then rewriting A in terms of those when it's possible to do so. I'm going to call this section Eigenstuff. Okay, so there are easy commands in Mathematica to produce these things. So let's look at again at our matrix A. So we could just compute the eigenvalues of A. And there they are. 3x3 matrix has 3 eigenvalues, generally, up to multiplicity. So you will always have eigenvalues that correspond to the dimension of the matrix. Now, it is not true that the number of linearly independent eigenvectors necessarily has to be the same. So we can check in this case if that's true. So let's look at the eigenvectors of this matrix. Okay, and it looks like we have 3 linearly independent eigenvectors as well. So the point of eigenvalues and eigenvectors is the diagonalization theorem or formula, which says that if you have the matrix P, which is formed out of the columns of P are the eigenvectors of A. So we're going to define the matrix P to be the matrix with columns that are eigenvectors of A. Then you can do this. You can write the equation P inverse dP, and if you do that computation, you get the matrix, P inverse AP, and if you do that, you get a diagonal matrix D, where the entries of D are the eigenvalues of A. This is called diagonalization. It means, in the language of upper division linear algebra classes, that A is similar to a diagonal matrix. That is, there's a change of basis that you can use where you can transform into a change of basis, act as a diagonal transformation, and then come back again to the original space. So that's kind of the theoretical version of what diagonalization is doing. But the language here is that A is similar to a diagonal matrix. Okay. All right. So how can I test this in this case? Well, the first thing is I need to have all of the eigenvectors be linearly independent from each other. And then when I look at them, I say, okay, well, I've got 1, 2, 3. If there's 3 of them and there's no zeros that show up in here, then I know that I've got 3 linearly independent vectors. The issue is that these are row vectors. So if those are row vectors, well, if I want to test this computation, I have to make sure that I'm working with the transpose of that. So let's define the matrix P to be equal to the transpose of the eigenvectors of A. So that has moved now the eigenvectors into the columns of A instead of the rows, or the columns of P instead of the rows of P. Now let's check our computation. We are supposed to be able to take the inverse of P, multiply it by A, and multiply that by P, and get a diagonal matrix D out that has these eigenvalues on the diagonal. Well, that's easy enough to do. The inverse of P, matrix multiplied, so dot A, matrix multiplied by P. If I run that computation, well, it doesn't look like a diagonal matrix because nothing is simplified. So as is many cases here, let's make sure that we force Mathematica to full simplify with the correct version of piping. And then if we take that and we put it into matrix form, we see that we get a diagonal matrix out the other side with precisely the condition that we said, which is that the entries of the diagonal matrix are the same as the eigenvectors or the eigenvalues of the matrix that we computed already. So diagonalization is an incredibly powerful tool, the beginning of a lot of ideas called matrix factorization, where we take a matrix and we rip it into small, structurally useful pieces. And every factorization that you learned in linear algebra has a corresponding command that will allow you to do that inside of Mathematica, at least the super important standard ones like the QR factorization or the LU factorization, for example. All right, so this is where we're going to leave this lesson. Where we're going to look at when we talk about things next time is more sophisticated things we can do with the linear algebra that we see inside of here. So in particular, we're going to look at things like matrix norms, and we can look at things like the singular value decomposition. And we might look at block matrices and the way that Mathematica can be used to manipulate and work with block matrices, which is another very powerful thing to be able to do. All right, so get started on the notebook and the book. This week, I want you to keep in mind that the book is incredibly thin on these ideas, and the notebook is very rich with about 10 years of problems contributed by various mathematicians in the department that have taught this course to give you a lot of different flavors of the way that Mathematica is used in linear algebra. In my own work, Mathematica is a key tool for working with matrices because, as we all know, matrix computations are tedious and long and error prone. So this is one of those places where you can really get some ground out of familiarity with Mathematica, and I hope you guys will engage with these problems with the enthusiasm that I had in talking about them. All right, so I'll see you for the next lecture.